All right, so today we're diving deep into something that I think a lot of you grad students out there are going to find pretty interesting.
Oh, yeah.
Yeah. Methane dry reforming. Taking those two greenhouse gases, methane and carbon dioxide,
Oh, okay. Yeah.
and turning them into syngas.
Right, right.
It's a pretty hot topic.
Yeah, and not just because the reaction runs above 700 degrees Celsius.
Exactly. Well said. So,
Well, I think what's fascinating is this isn't even a new idea. Scientists were looking into this back in the mid-20th century.
so why isn't it more widespread then? I mean, why isn't everyone doing this in industry? What's holding it back from being, a major player in all this climate change stuff?
So it really comes down to the catalyst.
Okay.
Methane dry reforming has a couple inherent challenges that make it really tough to scale up. One of them is it's a super endothermic reaction, so it needs a ton of energy to even get going.
Well, I bet that high temperature also plays a role in the second challenge you're about to tell me about.
You bet it does. At those high temperatures, you get something called coking. So basically, carbon just starts building up on the surface of the catalyst.
And I'm assuming that's not good.
No, not good at all. It's
Right.
like a clogged fuel line. It just hinders the reaction and reduces efficiency. Basically, the catalyst dies.
So we need a ton of heat. And that heat causes problems for the catalyst. That sounds tough. But wait, there's more, right?
You're right. There's also the Boudouard reaction, where the carbon monoxide kind of starts getting friendly and forms even more carbon deposits. And then you got the reverse water gas shift reaction. And this one, it messes with the composition of your syngas, which can be a problem depending on what you're trying to do with it.
Sounds like a high-maintenance reaction.
Yeah.
So how do we fix it? How do we make this work?
That's where things get really exciting. And this is especially true for all of you nanomaterials folks out there. It's all about manipulating that catalyst at the nanoscale.
Okay, so before we get into the nano stuff, let's just quickly go over the chemistry of this reaction. I mean, our listeners are familiar with the basics, but it's good to just have a little refresher, right?
Absolutely. So the basic reaction is pretty straightforward. One methane molecule reacts with one carbon dioxide molecule to make two carbon monoxide molecules and two hydrogen molecules.
Okay, so there's our syngas, 2 carbon monoxide and 2 hydrogen.
Exactly.
Sounds pretty simple on paper, but clearly it's not.
No.
So what's the first thing that comes to mind when we talk about optimizing the catalyst for this? For me, it's got to be the choice of metal.
That's a great place to start. The metal is like the heart of the catalyst. And nickel's the go-to choice.
Okay.
It's active, it's relatively inexpensive, and it's been studied a ton.
Sounds perfect. But wait a minute, we talked about coking, and I have a hunch nickel might be a problem child.
Yeah, you're catching on. Nickel does tend to have a bit of a coking problem with this reaction. That's why there's so much research looking at how to tweak nickel catalysts to make them more resistant to carbon buildup.
I'm sure our listeners are dying to hear about those tweaks, but before we get into that, what are our other metal options?
Well, when it comes to resisting coking, the noble metals are king. Things like ruthenium, rhodium, platinum, palladium.
Yeah, but those probably come with a noble price tag, right?
You got it. And cost is super important, especially when you're thinking about scaling things up for industrial use. So you got to find that balance, right? Cost and performance.
Right.
There's also cobalt. Kind of sits in between nickel and the noble metals, both in terms of activity and cost.
Okay, so we have a good amount of options here.
Yeah.
But choosing a metal is just step one, right?
Yeah, for sure. The metal's just one part of the puzzle.
Got it.
That support material that the metal sits on is also super important.
It's all about that foundation. Just like building a house, got to have a solid foundation.
Exactly. And there's a whole world of materials to explore for that support.
This is where things get really interesting, especially for those of us who are, fascinated by material science. But you know what? Let's save that discussion for part 2.
Sounds good.
Don't go anywhere. We'll be right back. Welcome back to the deep dive. So before the break, we were really getting into the whole catalyst design thing for methane dry reforming.
Right.
And especially the support material.
Yeah.
It's not just, sitting there doing nothing, is it?
Oh, no, not at all. The support is think of it as the foundation for your catalytic house.
Okay.
It really influences the metal, how it spreads out, how stable it is, even how active it is.
So what are some of the common ones? The common support materials that people use?
Well, one of the most popular ones is alumina.
Okay.
Alaro.
Got it.
It's really easy to get. It's relatively cheap. And it's got pretty good thermal stability, which is super important for this reaction because of those high temperatures, right?
Yeah, of course. 700 degrees Celsius.
Yeah,
but
yeah.
there's got to be a catch, right? I mean, we've been talking about coking this whole time.
Yeah.
And I have a feeling alumina might not be the best at preventing that.
You're right to be suspicious. Alumina, yeah, sometimes it can actually promote coking, depending on the conditions.
I don't know.
The surface can be a little too friendly to those carbon atoms.
Oh, so it's like that friend who means well but enables bad habits.
Exactly. So if we want to keep those carbon atoms in check, Ceria is a good option.
Syria?
Yeah, CEO. It's really cool because it can actually store and release oxygen.
Oh, wow.
And that helps to, like, oxidize the carbon deposits and keep the catalyst surface nice and clean.
So Syria is like the designated driver of the catalyst world.
I like that.
What else? What other support materials are there?
Well, zirconia is another good one, ZRO.
Yeah.
And this one is known for its super high thermal stability.
Oh, yeah. We definitely don't want our catalyst melting in those temperatures.
Exactly. We need it to hold up under pressure.
Yeah, for sure. So are there any supports that, like, actually boost the activity of the catalyst, not just, keep it from falling apart?
Absolutely. Carbon-based supports are getting a lot of attention for that.
Oh, interesting.
Yeah, things like graphene and carbon nanotubes.
There you go.
They're really great conductors, both heat and electricity, so that helps to move electrons around during the reaction, and that can really boost the efficiency.
Wow. So it's amazing how the support material can really change how the catalyst works. It's like pairing a singer with the right band to, like, bring out their best performance or something.
Yeah, I like that analogy. And just like we have lead singers and backup singers, we can also, tweak our catalysts by adding promoters or alloying different metals together.
Okay, so let's talk about promoters first. What exactly do they do?
Promoters are like, how should I put it? They're like the catalyst's hype team.
Okay.
They boost its performance in specific ways. For example, we can add alkali metals like potassium or sodium, and that actually helps to suppress coke formation.
Oh, wow. How do they do that?
They kind of mess with the electronics of the catalyst surface and make it less attractive to those carbon atoms.
So they're like bouncers at the Catalyst Club.
Yeah, keeping the riffraff out. And then we have alloying. That's like, it's like creating a supergroup of metals.
Yeah.
You take two or more metals, you combine them, and sometimes you get these really cool effects that boost the performance of the catalyst even more.
So what's a good example of a metal alloy that works well for methane dry reforming?
Well, a nickel-ruthenium alloy is a really good one.
Nickel-ruthenium, okay.
It combines, the high activity of nickel with the coke resistance of ruthenium.
So it's like taking the best parts of both.
Exactly. So you get a catalyst that's both really effective and really durable.
I'm starting to see how much work goes into designing these catalysts, It's not just throwing a bunch of metals together and crossing your fingers.
Absolutely not. It's a delicate dance, really.
Yeah.
You're trying to balance all these factors, activity, selectivity, stability, and of course, cost.
Right.
And with nanotechnology, we can really, control these factors at a level we never could before.
So we've talked about the metal, the support, promoters, alloying. Is there anything else we can do to optimize these nanocatalysts?
Well, one area that's really hot right now is controlling the size and structure of the nanoparticles themselves.
Okay.
I mean, think about it. If you have a big chunk of metal,
Yeah.
it's not going to be nearly as active as if you take that same amount of metal and divide it up into tiny, tiny nano-sized particles.
Right, because there's more surface area for the reaction to happen.
Exactly. It's like having more dance floor space for the methane and carbon dioxide to react with the catalyst.
Love that analogy.
Yeah.
But I'm guessing there's a downside, right?
There is. The problem is those tiny nanoparticles, they're so small and energetic that they want to stick together, especially at those high temperatures, and that's called sintering.
And sintern's bad.
It's bad because when they clump together, their surface area shrinks.
Oh, right. So less dance floor space.
Exactly, and that makes them less effective.
So how do we stop that from happening?
Well, there are a bunch of different techniques we can use to kind of control how the nanoparticles behave.
Like what?
One way is to use a porous support material
Okay.
with very specific pore sizes. This helps to keep the nanoparticles separated, like they each have their own little apartment.
I like that. Each nanoparticle gets its own tiny house.
Yeah. Another strategy is to coat the nanoparticles in a protective shell,
Okay.
so they don't actually touch each other directly.
It's like each nanoparticle gets its own little bubble wrap suit.
Exactly. And then you have the really cutting-edge stuff, single-atom catalysts. This is where you take it to the extreme.
Wow, okay.
And you disperse individual metal atoms on the support.
That's amazing. But it sounds really difficult.
It is. It's very challenging. But the idea is that if you can get every single metal atom to act as a catalytic site,
Yeah.
that's like the ultimate in efficiency.
So single atom catalysts are kind of like the holy grail of this whole thing.
In a way, yes, but they're still very much in the early stages of development.
So much cool research being done. This is fascinating. But we've talked a lot about the catalysts themselves.
Right.
The different support materials, the nanoparticle size and structure, all that stuff. But how does this actually translate into the real world? Like, what's the future of methane dry reforming? How does it fit into all this talk about sustainable energy and a circular economy?
That's a great question, and I think it's a perfect segue to the final part of our deep dive.
Okay, so stay tuned, everyone. We'll be right back. And we're back for the final part of our deep dive into methane dry reforming. We've talked about the challenges, the chemistry, all those amazing advancements in catalyst design.
Right, right.
But let's zoom out a bit now. Look at the big picture.
Okay.
Where does methane dry reforming fit into this whole idea of, a sustainable future?
Well, if you think about it, methane dry reforming could be really important for moving towards a circular economy.
Circular economy. Oh,
Yeah, it's not just about, getting rid of greenhouse gases. It's about making sure that waste turns into something useful, something valuable.
yeah, that's a really powerful idea, especially now, with climate change and all the worries about running out of resources.
Absolutely.
So how does methane dry reforming actually contribute to that? Can you give us some specific examples?
Okay, so one area is biogas reforming.
Biogas reforming. Okay,
So biogas comes from organic waste, right? Like stuff from farms or landfills. And it's got a lot of methane in it.
got it.
We can use methane dry reforming to turn that biogas into syngas.
Okay.
And then that syngas can be used to make a ton of different products.
So we're taking something that would have been thrown away
Exactly.
and turning it into something useful.
Exactly. It's a perfect example of closing the loop.
I love it. Are there other areas where methane dry reforming can make a big difference?
Oh, yeah, for sure. Um, think about power-to-gas systems.
Power to gas. Okay.
So we can use renewable energy like solar or wind power
Yeah.
to make hydrogen through electrolysis. And then we can use that green hydrogen with methane dry reforming.
Yeah.
And that lets us adjust the composition of the syngas.
Oh, interesting.
Yeah, and make it more versatile,
Yeah.
usable for a wider range of things.
So it's like we're storing that extra renewable energy.
Yeah, kind of like a renewable energy battery.
That's awesome, especially with everyone talking about green hydrogen these days.
Right. It could be a game changer.
Totally. So methane dry reforming can connect renewable energy to the chemical industry.
It has the potential, yeah.
That's amazing. What about, more traditional uses of syngas, like making fuels? Can methane dry reforming compete there?
Oh, definitely. Syngas from methane dry reforming can be used in something called the Fischer-Tropsch process,
Fischer-Tropsch. Sure.
and that makes synthetic fuels.
Interesting.
And here's the cool part. The methane and carbon dioxide we're using, we can get those from renewable sources.
Oh, right, like the biogas we were talking about.
Exactly. Or we can capture them from industrial emissions. So we're talking about a way to make carbon neutral fuels.
That's a huge deal. But let's be real for a second. What are some of the things that still need to be worked out? Before methane dry reforming can really take off.
Well, catalyst deactivation is still a big one.
Yeah, we've talked about that a lot.
Coking and sintering, those are tough nuts to crack. We've made a lot of progress designing better catalysts,
Yeah.
but there's always room for improvement.
Always looking for that perfect catalyst.
Exactly. But it's not just about the catalyst.
What else?
We need to make the whole process better, more efficient,
Okay.
like better reactor designs that don't need as much energy. And finding ways to integrate the process with renewable energy sources and carbon capture tech, that's going to be really important if we want to make it truly environmentally friendly.
So there's still a lot of work to be done.
Yeah, definitely. But it's exciting work.
Totally.
Huh.
So what's your message for our listeners? The future chemists and material scientists who are going to be working on all this.
I think the coolest thing about methane dry reforming is that it brings together so many different areas. Chemistry, material science, engineering. It's like this perfect melting pot of disciplines.
I love that.
There are definitely challenges,
Right.
but there's also a huge opportunity to make a real difference.
Yeah.
If we can design even better catalysts, optimize the process, and really figure out how to integrate it into the bigger system, we can make methane dry reforming a key part of a more sustainable future.
That's a great message to end on. Thanks so much for taking us on this deep dive into the world of methane dry reforming.
My pleasure.
It's been a really fascinating journey. For our listeners, don't forget to check out the show notes for more info and some links to further reading on this topic. And until next time, keep exploring, keep asking questions, and keep pushing the boundaries of what's possible.